So, can a computational model accurately describe the motion of an object, in this case a tennis ball, moving with a constant velocity based on physics principles? To do this, I will first extract data from observations. Then I will make assumptions based on physics principles. After, I will take both the data I've extracted from my observation and my assumptions and put them into a computational model. Then I'll compare the data in the computational model and from my observational data to reach a conclusion as to whether or not a computational model can in fact accurately describe the motion of an object moving with a constant velocity. So, from this observation, I just extracted the following data. All motion was in one dimension in the x direction. The observation start time was 0 seconds, and the tennis ball's initial position was at negative 0.017 meters in the x direction. The tennis ball's initial velocity was negative 1.357 meters per second in the x direction. The time of the last observation was set 0.709 seconds, and the mass of the tennis ball was approximately 0.057 kilograms. Now, Newton's second law tells us that force equals mass times acceleration. From one of the constant acceleration equations, we know that final velocity equals initial velocity plus acceleration times time. So for constant velocity, acceleration has to equal 0. Therefore, the force equals 0. The sum of the forces have to equal 0, or the net force has to equal 0. It says the same thing. And in vector notation, force can be written this way. Also, we know for constant velocity that there is no change in momentum. So for the computational model, I took the base code and put in my observational data. The ball's mass was approximately 0.057 kilograms. And here is the ball's initial position in vector notation, the ball's initial velocity in vector notation. Then, for the while loop, I put that while time was less than 0.709, and also while the net force in vector notation was 0, and then the ball's velocity equals the ball's velocity plus the net force over the ball's mass, which is acceleration, plus the change in time, or times the change in time. From this data, I put both my observational and experimental data into a position versus time graph. The blue line represents my experimental observations, while the red line represents my computational model's predicted observations. The slope of the lines represent the velocity. The red line is perfectly straight, just as the velocity is predicted to be constant. At the very end, there's deviation between the blue and the red lines. The experimental line slope becomes slightly less steep. This is because the ball slows down, probably because of friction on my table. But for the most part, at the beginning of the experiment, the lines match up very closely. So overall, I would say that the computational model does in fact predict accurately the object's velocity. And if there were no friction, I would say the lines would be spot on.